we have constructed the pushdown automata for given context-free languages, and you know that context-free language can be described with the help of the context-free grammar. So if you are given some context-free grammar, and if you are asked that, okay, for this context-free grammar, how I can construct the pushdown automata. So here we will see that if you are given some context-free grammar, which we denote by writing the CFG, then how we can obtain the pushdown automata. So we are going to see the conversion from context-free grammar into the pushdown automata. Now, if you have the pushdown automata, then we know that PDA, pushdown automaton, accept the context-free languages, and for every context-free language we will have the context-free grammar. So here, if we go for the reverse, then we will see that how we can obtain the corresponding context-free grammar from the given pushdown automata. Here actually our aim is what? If you are saying that if you are going to obtain the if you are able to obtain the pushdown automaton corresponds to the context-free grammar, then the language accepted by the context-free grammar will be same, and the language accepted by the pushdown automaton is same. And if you are converting the PDA to the grammar, this means the language accepted by the pushdown automaton is same as the language generated by the context-free grammar you have obtained from the given PDA. So this we are going to see the conversion. So first we see that how we can convert a given context-free grammar to the PDA, means a PDA corresponding to the given context-free grammar. We can denote the grammar by writing the G is equal to V sigma S and P. Okay. So language generated by this grammar is denoted by writing the LG, and the PDA we can denote by writing the M, which is the Q sigma tau Q0 Z0 A and delta. This is the pushdown automaton, and the language accepted by the pushdown automaton is denoted by writing the LM. So here actually we want to obtain the pushdown automaton corresponds to the given context-free grammars, and this means the language, whatever the PDA you are going to obtain from the given context-free grammar, then the language accepted by the PDA, which is the LM, is same as the language accepted by the grammar, means LG is equal to LM. So we have the theorem. Let G is equal to V sigma SP be a context-free grammar, then there is a pushdown automaton M, so that LM is equal to LG. This means we are supposed to obtain the pushdown automaton corresponds to the given grammar, so that the language accepted by the PDA pushdown automaton is same as the language generated by the grammar G. So how we can do this? So here we are given the context-free grammar, we are given the G. So here we are given the context-free grammar G, and we know that the grammar G has V sigma SP. This is the 4 tuple, and we are going to obtain from this context-free grammar, from the given context-free grammar to the PDA, which is M is equal to Q sigma tau Q0 Z0 A delta. So here actually we have language, since we are going to talk about the language of PDA and language of context-free grammar is same, hence we have the sigma here, sigma is remains same, and we need to decide the number of states in the PDA. We need to decide what symbols we need to keep onto the stack, and we have chosen the Q0 as the initial state and Z0 as the initial stack symbol. We need also to decide which one should be the fun state, and finally we have to show the transitions. So converting the context-free grammar into the PDA, this means we have to show what should be the states of the PDA, and what should be the contents of the stack, what symbols we can store onto the stack, and which of the states among which one is the final state from the given queue, and what should be the transition function of this PDA, so that the language accepted by the PDA is same as the language generated by the grammar G. So this we need to obtain. So for conversion, actually, whenever you are going to convert the grammar into the PDA, then the PDA m is equal to q sigma tau q0 z0 a delta is constructed as follows. We are going to construct, and for construction, actually we need to see what should be the states of the PDA. Means we need to decide what should be the states of this PDA. So for construction of the PDA from the given grammar, actually we need 3 states only. So one is q0, q1 and q2. So whatever grammar you are given, you can obtain the PDA corresponds to the given grammar using only 3 states, q0, q1 and q2. And here q0 is the initial state and q2 is final state. So we have the final state A is the set of final state, and here we have only one final state, which is the q2. So we have only the q2 is the final state. Now how we can see the transitions actually. So actually we have decided the q, we have decided q, okay, and we have sigma is remain same. Now we need to see the stack symbols. What should be the stack symbols? And then we have to show the transitions delta. So see that if you are given some grammar, like you have s derives a b, okay, you may have the production rules in the grammar s derives a b, and s is the start symbol. You may be given the string x, say for example x, we say that x b b a, you may be given like this, and you will be asked that whether this string can be generated by the grammar or not. So if you are given you are having the grammar, and once you are having the grammar, then you may have some string, say x is equal to a double b. This is just for the example. So, and we need to verify whether this string, this sentence is in the language of this grammar or not. So actually what we need to do, we need to start from the start symbol. Say for example this is the start symbol s, and since we have the production since a b, so we can replace s with small a capital B. So small a capital A, and here we assume that as a b, these are the, you have the as a b, all such are the non-terminals we have, and here you have the a and b are from the sigma. So we have the sigma alphabet, and a and b are the element of the sigma. So if you are given some grammar, say s, and you have given the string x a double b a, and you will be asked that okay, yes, can we verify whether this string can be generated by the given grammar or not. So naturally we start from the start state. Okay, now see, so what happened, s derives a b. Now you see that you want to generate a double b a, and here this starts with a b. So input is a here and input is a here. This is matched. So this first a is matched with this input. Okay. Now our target is to replace the non-terminals a and b, so that we should be able to obtain the double b a. So you may have the production in the grammar, like you may have the production like A derives, A may derive, say for example, double B. You may have the production, A derives double B. So if you have the A derives double B, then you can have now A can be replaced with the, say for example, double B. And now you have the non-terminal B. Now you can see that you have already matched A, and now you have B, and here also you have the B, then next B, and here also you have the B. So A double B you have matched correctly, and now you have the non-terminals B, and we want that the next symbol is A. So you have to see the production. What is the production rules for the non-terminals B? And if for the production of the non-terminals B, if you have like this, B derives either A or you have the null. So if you have the production like B derives A or B derives null, then we can use the production rules. B derives A, then you are having the string A double B, and B is replaced with the A. Now you see that last A is also we have matched. So this is the string we have A double B A and A double B. You wanted to verify whether X is equal to A double B is in the language or not, and starting from the S you are able to find out, you are able to generate this string A double B A. Hence A double B A is in the language. Okay, so what we have done here, actually we have started from the start symbol S, and you have, according to the production rules, this is the grammar G, this is the grammar G, and according to the production rules of this grammar, we have replaced the S. So starting from the S, we have obtained the AAB, and once you have the terminal symbols A, then we will see that in the input we have the A, and here is also the A. So this is the match. Now our target is to match the next subpart of the given string, substring. Like we need to match double B A. So we will see the production rules for the AAB. So this is corresponds to the leftmost derivation. So we are following the leftmost derivation. So whatever non-terminals appear at the left, we are going to replace it first. And after replacing, we have the string, you will have the string of terminals and non-terminals. And if you have the terminal symbols, you can see that in the given input whether it is matching or not. If yes, then you can go for the next one. So here you are given the context-free grammar. We have given the context-free grammar, and from the given context-free grammar, we are going to obtain the PDA. So now for the case of the PDA, actually we need to think that what should be the stack symbol. So what you need, you say that what should be the stack symbol? See that you have the stack as the memory in case of the PDA, and you have to store the non-terminals. Whatever non-terminals are there, you have to store the non-terminals, so that once the non-terminals will be at the top of the stack, then you have to replace with the corresponding production rules. And once you have replaced the production rules, like once if you have the say for example you have the stack like this, and at the bottom we have the initial stack content, which is the Z0, and you have to store as first thing is that you, since the construction of any sentence is begin with the start symbol as, so first non-terminals you have to push onto the stack is, which is the S. Now you see that you have the S on the top of the stack. So our first job is what? We have to replace this S with the given production rules. So once you replace this S with the given production rules, then you will have the situation like this. S can be replaced with AAB. So you have A, and then B. So AAB. Okay. Now A will be, A is corresponds to what? A is corresponds to this is the corresponds to the top of the stack. So A is corresponds to the, this A is corresponds to the top of the stack. So you will have the top, and next top to top is A. Then you have the B. So S is replaced with A, B. So you have the S, and you are going to replace S with A, B. Okay. So you have the top of the stack becomes A, and you are given the input X. X is A double B A, and leftmost symbol of this string is A. So you have matching is done. So you have to delete. So you have to delete this. Now once you have deleted, then the top of the symbol is what? Again you have the non-terminal. So if this is the non-terminals, and see that the first symbol you have already matched. Now you have the non-terminals A. So if the top is the non-terminals, stack top contains the non-terminals, then actually without reading the input, without consuming the input, what you need to do? You have to replace this top of the symbol, top of the stack symbol, which is the non-terminals, with the corresponding production rules. So once you replace this A with corresponding production rules, then you will have the situation that A is replaced with double B. So you have the double B like this. Now you can see that you have next input is B, and top of the stack symbol is B. So you have matching. Yes, you wanted to generate. Now next input is B, and top of the symbol is B. So this is also matching. Now the top will becomes this, and this is the non-terminal B. So you can replace this. So in the given grammar, whatever non-terminals are there, you have to store onto the stack. As well, whatever input symbols are there, you have to store onto the stack. So that's why we have the stack alphabet contains these symbols, all non-terminals B, union, every input symbol, union, we have the initial stack contents, which is the Z0. We assume that Z0 does not belongs to either, this should not be in either in the non-terminals, or it should not be in the terminal symbols. So Z0 is not a member of this set. Okay, so this we are going to assume. So here we have decided the Q, we have decided the A, and we have decided the tau. Now actually you need to give the transitions. How you can make the transition? So see that your machine will start from the Q0, and the first job of our first job is what? Our first job is to keep start symbol S onto the stack, and while doing this you have to go to the state Q1, and in the state Q1 we have to simulate the derivations, which is corresponds to the leftmost derivation. So what we need to do? We have the transition functions. So we have the, you are in the state at the beginning, you are in the state Q0, your machine starts from the Q0, and without consuming the input, we don't have the input, we don't require to consume the input, and top of the stack is what? Z0. So the transition function is defined like this: delta Q0 null Z0 is equal to, your machine should go to the state Q1, and we are not going to modify the, you are going to the state Q1, and we are pushing S onto the top of the stack, means Z0 is replaced with S Z0. This is our first job. This is the transition of your PDF. Now next, if you are at the state Q1, if you are at the state Q1, then what happened? You are having the top of the symbol is, top of the stack symbol is the start state, and starting from the start state, you are going to simulate the derivations. So our actually, what is the intuition is that whenever we have the start state as, our intuition is to replace this S with the string of terminals. So on behalf of the given input strings, we have to see that whether we are able to replace this S with the string of terminals only. So actually at the beginning you will push some strings instead of the deletion of the S. At the beginning you will push some more symbols, maybe the terminals, the string of the terminals or non-terminals both, onto the stack. Then one by one you are going to match from the given input, and if the given input is in the language, then you will have whatever you have pushed onto the stack, you will be able to delete everything, and hence S will be deleted. So once S will be deleted, then the top of the stack becomes Z0. So at the state Q1, once you are having, you are at the state Q0, and your machine starts from the state Q0, and you are going to the state Q1. You have the Q1, and this is, you have the Q2, and Q2 is the final state we have decided. So from the Q0 you are going to the state Q1, and going to the state Q1 means without consuming the input, top is Z0. You are replacing this Z0 with the S Z0. Now once you are at the Q1, and if you are able to see that once you have the top of the symbol is S, and starting from the start symbol you are simulating the derivation, and once you have obtained the given strings, whatever you have the given input, and for the given input, if you are able to delete this S from the stack and the top will become Z0, then it means that the given string is in the language, and hence from the Q1 if you see that top is Z0, then you can go to the final state. So the next transition is what? So starting, if you are at the state Q1, input is null and top is Z0, then you are going to the final state. Final state is Q2, and we are not going to change this top, so you have the top symbol is remains same. So this is the transition. Okay. Now we have the third transitions. So what you have to do at the state Q1, for every A belongs to V, we can define the transition delta, or at the Q1 input is null and top of the symbol is A, where A is some non-terminals. Then we again remain in the state Q1, and we replace the non-terminals A with the string alpha. And what is alpha? Such that A derives alpha is a production in the grammar, given context-free grammar G. So if alpha is a production rules, if A derives alpha is a production rules in the given grammar G, then this non-terminals A can be replaced with the string alpha. So this we do, and the leftmost symbol of this alpha will be in the top. And again you will see that if the leftmost symbol is in from the sigma, then you see that what is the input, and if the input is the same symbol and the top of the stack is same, then matching is done. You have matched and you can delete it. So fourth transition rules will be, for every A belongs to sigma, what we need to do? For every A belongs to sigma, delta Q1 A is equal to, you are remain in the same state, you are in the Q1 and you are going to delete it. So if you see that for every A belongs to sigma, so if input is A and top is also A, then you are going to match the symbols. So once matching is done, you have to delete it. So once you can delete, then you may have next symbol, next top to top may be the again the input symbol, or it may have the some non-terms. If it is the input symbol, then again you can see that whether the next input is the same as this top symbol. If yes, then matching is done, you can delete. And if the top of the symbol is the non-terminals like here, then you can replace the non-terminals with the string alpha, where A derives alpha is in the production. So these are the only 4 transitions. You have defined everything now. You are given some grammar and you wanted to convert the grammar into the PDA, and for the PDA you have defined the number of states, and we have 3 states only. In fact, for any given context-free grammar, if you go for the PDA corresponds to the given context-free grammar, then you just need 3 number of states, Q0, Q1 and Q2. And here Q2 is the final state, and you Q1, the state Q1 is generally, actually we are going to use the state Q1 for the simulation of the derivation, and state Q2 is the final state. When the derivation completes, when matching completes, then you have to jump to the final state. The first transition will be like this. The first one will be from the initial state. The first job is to push start symbol S onto the stack and go to the state Q1. This is the job of the first rules. In the second, once you are at the state Q1 and once you see that the top of the stack is Z0, then this means whatever you have pushed, everything you have deleted, and hence you have to go to the, if the input exhaust and top becomes Z0, this means matching is done, and hence this is the case of acceptance, and you go to the final state Q2. At the state Q1, you have 2 situations. The top of the symbol, top of the stack will be either the non-terminals or it may be the terminals. If it is the non-terminals, then we need to replace the non-terminals with the strings alpha, such that in the production rules of the grammar, that non-terminals derives the string alpha. So A derives alpha. So we have A derives alpha is, if A derives alpha is a production rules in the grammar G, then the A will be replaced with the alpha, and the leftmost symbol of this alpha is actually what? This is the top of the stack symbol. So leftmost symbol of the alpha will become the top now. Second situation, instead of the, if the top symbol of the stack is element from the sigma, means this is the terminal symbols, then you can see that what is the input symbol. If input symbol and the top of the stack symbol is same, then you can delete. Matching is done and you can delete. And this is the process you have to, this is the kind of transitions you have to do at the state Q. So 3 and 4, 2, 3, 4, these are the transition from the state Q1. The transition second is just to go to the final state, and 3 and 4 are going for the, we can use the 3 and 4 for simulation of the derivation tree. Starting from the start symbol by using the production rules of the grammar G, if you have the grammar G, and by starting from the start symbol by making the sequence of transition for the given grammar G, and if you are able to derive the string X, then what? This means X belongs to the language of the grammar G. This. If yes, this, then this. Okay. And if you have obtained the PDA corresponds to this grammar, then what? Your PDA should start from the initial configuration. And initial configuration of PDA is what? Your PDA start from the initial state Q0, and at the beginning you will be given the X, and the top of this symbol is only Z0. Okay, this is the contents of the stack, and by making the sequence of moves from the given machine M, PDA M, you will be able to reach the final configuration like this. Here you have the Q2 is the final state, and remaining input to be read is null, and whatever be the contents of alpha, such that Q2 belongs to final state A. Okay, and alpha is what? Alpha can be, alpha is any string from the tau star. So alpha can be any string from the tau star. So this is this is what? This is the initial configuration, and you have the initial configuration, and this is the final configuration. So starting from the initial configuration, you are able to reach the final configuration. So if in the given grammar, if in the given grammar G, if you have the situation starting from the start symbol S, if you are able to derive the string X by using the sequence of rules, by using the production rules of the grammar G, then you can say that X belongs to the language G. And if you have obtained the PDA, then your PDA should also, for the same string X, your PDA should start from the initial configuration, and by making the sequence of moves in the machine, your PDA is able to move this final configuration for this given X, and hence X is also in the language of. So in this way you can say that X also belongs to the language of PDA. So if you have obtained the if you have obtained the correct PDA from the given context-free grammar, then this must holds true. Okay, let us see one example. Consider this language L is equal to set of X which is taken from the AB clean star such that number of A in X is greater than number of B in X. Okay, so here actually instead of the language you are given the grammar. So instead of this language you will be given the grammar. So what is the grammar? What is the, since this is the context-free language, okay, so if this is the context-free language, then what is the grammar for this language? So we can go for the grammar. So this is the grammar for the given language. L is equal to X belongs to A with clean star such that number of A in X is more than number of B in X. We have the grammar, and the grammar rule says that S derives A, S derives AS, S derives B double S, or S derives SSB, or S derives SBS. So any strings you can generate. If you want to say, for example, if you want to go for the if you have the string like this A double B A, and if you have the string like this A double B AA, okay, so if this is the valid grammar and this is the valid string because number of A is more than number of B, so you will be able to obtain this string starting from the S. You want to obtain this X is equal to A double B A. So if this is the valid string and this is, if this is the valid, since this is the valid string of this language, number of A is more than number of B, so this must be generated using this grammar. So you can start from the start symbol S. So S derives, which production rules you can apply? You can see that which out of these 5 production rules you have to see one will you can apply the production rules, okay, one by one. So you may think that okay, you can apply the production rules like S derives SBS. So you can say S derives SBS. Okay. Then we need to obtain A at the beginning. So S can be replaced with using the production rule S derives A. So you can obtain S derives A, and you have the B and S. So A is matching and B is also matching. So AB is matched correctly. Now you have to replace S. So you have the non-terminal S, and S can be replaced with, you also need B here. So you can replace with this production rules B double S. So A, B, S can be replaced with B double S. Okay. And now see that by applying the production rules, you have the A, B, B. Now S can be replaced with A, and then you have the S. Finally, A, B, B, A. This non-terminal S can be replaced with terminal A. Now A double B double A. A double B double A. This is the string you have obtained. This is the X. And hence, since you have started from the start symbol, and by making the sequence of rules in the grammar G, you are able to obtain this string X. Okay, and hence this X belongs to the language of grammar. And this is the way you can say that, okay, yes, this is the grammar for this given language. So any strings you can take from this language, and you will be able to generate the strings. Now our objective is what? Our objective is how to obtain the PDA for this. So we have seen the construction of the PDA. Now we apply the rules. We have to go for the PDA, and once we go for the PDA, now we will have the three states, So one is Q0, okay, and then we will have the Q1, and then we will have the, so Q0 is the initial state. You can start from the initial state Q0, and the first transition is what? From the Q0 we need to go to the state Q1 without consuming the input, and top of this symbol at this point is what? Z0, and hence we can replace this Z0 with S Z0. We are pushing S onto the top of the stack. Now you are at the Q1 and the top of the stack is non-terminal, so we have to replace this non-terminal with the production rule. So here you can see that there are 5 production rules. So you can replace. So you can replace. You can say input is null and top of the symbol is S. Replace with A. Or input is null, top of the symbol is S, and S can be replaced with AS. Input is null, top of the symbol is stack symbol is S, and S can be replaced with B double S. Input is null, top of the symbol is S, and S can be replaced with SSB. Input is null, top of the symbol is S, and S can be replaced with SBS. So these are the 5 production rules we have. For the S we have the 5. So for this is the, you can see that now if you are at the state Q1 and the input is null and top is S, then you can replace with S can be replaced with the alpha, and alpha is here is what? A, because S derives A is the production. Since S derives A, S is also production, so you will also be able to replace S with AS. S derives B double S is also a production, so you can also replace S with B double S. S derives SS. Similarly, S can also be replaced with SSB, and S can also be replaced with SBS. So whenever you have top of this symbol is S, then you have the 5 possibilities, and machine will make the, if the string is in the language, then machine will be able to, there must be some correct guess of replacement, so that your machine will be able to reach the final state. Now if you are at the state Q1, and if your input is A, and top is also A, then matching is done, you have to delete. Since we have the two input A and B, so if input is B and top is also B, you have to delete. And once the derivation is over and your top of the symbol of the stack is becomes Z0, then you can go to the final state. So this null top of the stack is Z0, then you may not change the stack symbol, and now your machine is moved to the final state, and this is the final state of your machine. So when at the beginning you have pushed S onto the stack, and after the derivation you have completely removed whatever you have pushed, everything you have matched, and hence the top will become Z0. So once top will become Z0 actually, then you come to know that that your derivation is over, and you go to the final state. And once you are at the final state and you have matched correctly and your input exhaust, then you will see that okay, yes, the given input is in the language. So this is the PDA, and this is the PDA you have obtained from the given grammar G. So this is the way you can construct the PDA from any given grammar. So here you can see that starting from the start symbol S, by making the sequence of derivation rules, you are able to obtain the string X. And here we have seen X is equal to what? A double B double A. For X is equal to A double B double A, we have seen that starting from the S, by using the rules of the grammar, we are able to generate the string A double B double A, and hence A double B double A is in the language. And see that starting from the S, and this is the PDA we have obtained from the given grammar. This means starting your PDA must start from the initial configuration, and the initial configuration is what? Q0. Input to be read is what? A double B and double A, A double B double A, and A double B double A, and top of this symbol is what? Z. So this is the initial configuration. If for the given X, for this X, starting from the start symbol X, if this S, this string A double B double A is generated by using the production rules of the grammar G, then means this is in the language. And if this is in the language, then for the same input, starting from the initial, your machine must start from the initial configuration, and initial configuration of this machine is what? Q0 A double B double A for this string X, and at the big and top of stack contents is only Z0. The string contents in the stack is Z0. Starting from this configuration, your machine must move, by making the sequence a move, your machine must be able to move the final configuration, and final configuration of this machine is what? Q2, because Q2 is the final state, and remaining input to be read is null, and irrespective of the contents of the alpha, we don't worry about the alpha. Alpha can be any string from the tau star. So this is the final configuration. Say that you are at the state Q0, Q0 A double B, and then you have the double A, A double B double A, and Z0. This is the configuration. From this configuration, you can go to the configuration like you are at the state Q0 and your machine transit to the state Q1 without consuming the input. So A double B, and you have the double A, A double B, A double B double A, and here you are pushing S onto the stack. So S Z0, this becomes. And then from this configuration, okay, and here assuming that this is the M, so you can write here M, you write it. So now next is what? You are at the state Q1 and the top of this symbol is what? S. So you are not going to consume the input. So you have the A, double B and double A. The input to be read next is remain same, and your S is going to replace with the strings. So S is replaced with what? S is going to replace with S, B, S. This is the correct case for this. So S is replaced with S, B, S, and you have the Z0. Okay. So since S was in the top, so you are going to replace S with the production rules. Which production rules? S is you are going to replace with the production rules. S derives S, B, S. Now from this your machine can move to the state. Now S is again is the non-terminal. So you are at the state Q1. Still you are not going to consume the input. So A, double B and double A. Now S is replaced with the string A. We are using the production S derives A. So you are going to use S derives A. Okay. So we have A, B and S and this Z0. Okay. Now see, we are at the state. From this configuration you can go to the configuration like this. Again you can remain in the same state, and input is A and top is A. So you are consuming the input here. So B, B, A, A, double B, double A, and here the stack contents will be B, S, Z0. So input is A and top is A, deleted. Now from this configuration your machine can go to Q1. Now see that input is A and top is also B. So it is matched, and hence remaining input to be read is B, A, and here the stack contents will be now S, Z0. So now again you have the top of the stack becomes non-terminal. So your machine is not going to consume the input, and you are at the Q1 and input remains same, and you are going to replace this S. So you are going to replace this S with what? You are going to replace this S with B double S. So you have the B, S, S, and Z. Okay. Now top of the stack was S, and you have replaced this S with the B double S. You have used the production rules B double S, B double S, S derives B double S. Okay. So S derives B. So B is in the top now. So from this configuration, your machine goes to the state Q1. Now input is B and top is also B. So matching is done. So you are consuming the input. Now the remaining input becomes AA, and here the stack contains is SS, Z0. Here you are at the state Q1, and top of the stack is non-terminal, so you are not going to consume the input, and you are replacing S with the string S derives A. So you have the A. Okay. So we are having the A, and here you have the S and Z0. Now from this configuration, now you can see that you are at the state Q1, input is A and top is also A, so you are deleting, and remaining input becomes now A to read, and here the stack contents becomes as Z0. From this configuration, by making the moves in the machine, now you are at the state Q1, input is A, top of the stack is S, so S can be replaced with the production rules, S derives A. So you have the A and you can have the Z0. And from this you will go to the state Q1, input is A and top is A. Now the remaining input to be read is null, deleted. Okay, you are consuming and the top will becomes now Z0. Now from this configuration, from this configuration, your machine goes to the state Q2 and input is null. From Q1, top becomes Z0, so you can go to the state Q2. Remaining input to be read is null, and we are not going to change the top. And this is actually, this is the final configuration. Final. Okay, why this is final configuration? Because Q2 belongs to final state. So starting from the initial configuration, starting from this initial configuration, we are able to reach this final configuration. Starting from the initial state, so we are able to reach the final configuration. What is the string for which you are able to reach the final configuration? This is the string. For this string, now we are able to reach the final configuration, and hence this string is in the language. So you can say that A double B double A, this will belongs to the language of the machine. And since this was also generated by the given context-free grammar, and hence this is the way you are going to, every string which you can generate, since this is the, you have obtained the PDA corresponds to the given grammar G. So for every string which is in the language of the grammar, for the same strings, you will also be able to move to the final configuration starting from the initial configuration. And hence here you have seen that from the given grammar G, we are able to obtain the PDA like this. So if you are given the context-free grammar, then corresponds to context-free grammar, this is the way you can obtain the pushdown automaton that accepts the same language as the language generated by the given grammar. Okay.